Okay, so let's talk about direction, the second attribute of the Megatable PDF. So conceptual models, you've been dealing with conceptual models, you just haven't realized it yet. Conceptual models are those boxes and arrows that we use to make a visual representation of some sort of effect that we're investigating. So I'm imagining that hearing a joke will make people laugh. So that's the effect that I'm assuming that exists, right? And hearing a joke, I can measure that in an experiment by sending people to two separate groups. One group is going to be watching a TED Talk. The other group's going to be watching a joke, stand-up comedy, and that's going to be the treatment. The other one's just going to be the control group, right? The TED Talk is just a control group. A boring TED Talk with no humor. Then we can measure laughter in decibels. We can measure the audience level of decibels, right? Are they laughing a lot? Very loud laughter, not laughing at all, that awkward silence in the audience.
So very quickly, to the sound of Bossa Nova, let's discuss positive and negative relationships. Given our initial conceptual model, the more you hear a joke, the more you will laugh. That's a positive relationship. A positive relationship is usually represented by a plus sign. But if you don't see any signs, you can just assume that it's a positive relationship. That's sort of like the standard. Negative relationships, on the other hand, are represented by a negative sign. And that's showing you that the more you get this thing, the less you get that thing. So in this example, the more you smoke, the less white teeth you get.
Great. So let's think of the notion of symmetry and dependence. Some conceptual models can be asymmetric. So this can be very well exemplified with this conceptual model, age predicting income. You can measure age, for example, with completed years, right? So I'm 23 years old, and you can just ask that in a survey like we did before. Income could be the amount of dollars you make a year, right? So your salary, so the amount of money you make a year, which we could also ask in a survey, and then we could establish and see if that's the case. We could also plot these two in a scatter plot. So we could, for example, find all of the values of all the people of all the ages and find the values of all the people with all different incomes. Let me show you. The way that this would look like in a data set is, let's say you have variable age and you have respondent number 1, and we're going to say that respondent number 1 has age 19, and that's why he's right here. It's right, this green square that we see right here. That's respondent number 1. Respondent number 1 also has an income that's pretty low compared to everyone else. Okay, this is what we're doing. Each point in this scatter plot represents an age and an income, and you're just looking at that. Age here is what we call an independent variable. Why? Because there's nothing influencing age. Income here is the dependent variable because it's dependent on age, right? And the way that you calculate this and then you think about this is like, okay, the older I get, right? So the older I get, the more money I tend to make, right? Because you keep going, this pattern keeps going up. If you ever have a question of whether you're dealing with an independent or dependent variable, you just ask yourself this question. Does income have arrows pointing towards it? Yes, so it's dependent. Does age have arrows pointing towards it? No, so it's independent. Very important. Every time we're establishing an asymmetric relationship, you must have a really good reason to believe that things only go in one direction. And here we actually do, because age predicts income. But when was the last time that you made a lot of money and suddenly you became very old? It doesn't happen. So age is something that's usually not affected by anything other than time itself, which is sort of what it's measuring. So it's kind of pointless for age to ever be a dependent variable. Age will probably almost never be a dependent variable. So now, we also have this other kind of relationship, which is called a symmetric relationship, which is a situation in which the arrow goes both ways. So, for example, how much time you spend on TV and how much time you spend on the internet. You could measure that in minutes. So I can measure how many minutes you spend watching TV. If a researcher to your home with a stopwatch and they're just like watching you the whole day and counting the total amount of time you're watching TV and watching the internet in minutes, they can give me that easily, right? So the thing that I want to show you here is that time spent on TV and time spent on the internet, they should probably look like something like this, The more time you spend on TV, the less time you spend on the internet. And the more time you spend on the internet, less time you spend on TV, right? Because the new generation is going to the internet and they're watching less and less television. This is a situation in which we can ask ourselves the question that we just asked before. Does the box have arrows pointing towards it? Yes, so it's dependent. Yes, so it's dependent. They're both dependent. It's a situation where we call them codependent variables. Now, there are other types of models. For example, starting with this asymmetric model with age as independent, income as dependent variable, And you can ask yourself, but why? Why is that happening? So we can add this third variable, years of work, which makes us go, that's why. So this third variable that we're adding here is a mediator, right? This is a mediation. And the idea of a mediation is that a mediation explains why, right? It's not that suddenly you will turn older and then you will make more money. No, it's that when you turn older, you have more years of work, and companies tend to reward their employees with higher salary based on their time working. Everything makes sense now, and that's the feeling that you should have when you're dealing with a mediation. But there's more. I don't know if you ever heard of Monty Python, the British comedy group from a while ago, I think the 70s. They are known for having this very British humor, very nonsense humor, right? And so you could start from this idea of like, hearing a Monty Python joke will make people laugh, right? So I could conduct a study and see, oh, okay, if you hear a Monty Python joke, you laugh or you don't. And I could assess that. And you probably have that friend who will come to tell you, man, British humor is amazing. I really love British humor. And well, sure, it might be great, but that's not true for everybody. That's one thing that you could say. So that's when we add this third variable, a person's type of humor. Notice how this arrow here looks a little weird. We're going to talk about that in a second. And here we're going to have two levels, dark humor or nonsense humor, which is more the British humor. This is a moderation, and a moderation splits your conclusions. Bear with me. I'm going to tell you what it means. What we're going to do is we're going to repeat the study, but this time we're going to select only people with nonsense humor, and we're going to test if hearing a Monty Python joke makes them laugh. And then we're going to find out that they laugh, right? Because they're into the British nonsense humor. It's great. Now we're going to repeat the same study with people with dark humor. Okay, so we're just selecting these people of our data set. They're going to hear a Monty Python joke, and we're going to see if they laugh. Do they laugh? No, they don't, because it's not their type of humor. They're going to say, oh, this is too bland. I don't like it. So this is why moderation splits your conclusions. Instead of having one single conclusion, you have one conclusion for each of the groups listed in your moderator. We have one conclusion for nonsense humor, one conclusion for dark humor. We're literally repeating the same study with a population of only people with nonsense humor and with a population with only people with dark humor. Great. A deep breath. Now let's talk about dry mix. This is an acronym, dry mix, as you can see here. Dependent responder y-axis, manipulating independent x-axis. And you can use this if you ever forget which one is which, okay? So in an asymmetric relationship, you're going to have for example, age and income. Which one is the independent? Well, the independent is the one that is manipulating, right? So age is the independent variable. Age is manipulating it, so it's also the independent variable, and it stays in the x-axis of your scatter plot. It's sort of a standard that we chose to use, okay, worldwide. Now, on the y-axis, you're going to have a dependent variable, which is going to be income, right, which is responding to age, right? So the older you are, you're going to get a certain amount of money. That's going to be represented by the y-axis, which is the vertical axis, okay? So x-axis, always the horizontal, y-axis, always the vertical axis. We're also going to use the letters x and y to write equations, so it's very useful if you remember the dry mix later on. Cool? Gratitude breaths, and that's it. I'll see you next time.